How do you use the Laplace transform to solve this differential equation? So let's say you are given this differential equation y prime of t minus 2 times y of t, and this is equal to 0 with the initial condition that y of 0 is equal to 1. So we want to use the Laplace transform to solve this differential equation. So to solve this one, you can use separation of variables, but how do you use our Laplace transform to solve this differential equation? To solve it using Laplace transform, we will have to take the Laplace on both sides of this differential equation, and that means that we will have to take the Laplace transform of the derivative of a function y prime of t. We know the Laplace transform of y of t. So the Laplace transform of y of t, this one is equal to capital Y of s, right? But we do not know the Laplace transform of the derivative of the function. So for us to be able to use the Laplace transform to solve this differential equation with initial value condition, we will have to establish the value for the Laplace transform of the derivative of this function. So I'm going to go ahead and then derive the Laplace transform of the derivative of this function, and then later on we can use that to solve differential equations. So the importance of this tutorial is to be able to use that to solve differential equations. So the main idea or the importance of doing this is to be able to use Laplace transforms as an alternative to solving differential equations with initial value conditions. So the Laplace transform, we already know from the definition, the Laplace transform of the derivative of a function y prime of t. This is the integral from 0 to infinity of e to the negative st. And this is multiplied by what we are seeking to transform, which is y prime of t and then dt. Right, so the task now is to find the value of this integral. So to solve that integral, we will have to use integration by parts. So integration by parts, I normally do the tabular method or the DI method, D for differentiation and I for integration. So I am going to differentiate e to the negative st. This is plus, next one is negative, and I'm going to integrate y prime of t like this. So differentiating this one with respect to t, that is going to be negative s multiplied by e to the negative st. This is the derivative of this function. And now integrating this is the y prime of t. That is the derivative of y with respect to t. And we are integrating the function with respect to t. So the integral of y prime of t is just y of t. So the integral is just the same thing as antiderivative. So the integral is just going to sort of like cancel the derivative, leaving the original function y of t. So this is what we have. Normally we will now have to multiply diagonal terms. We are done with the integration, but when we multiply terms horizontally, there is an integral in the process. Alright, cool. So now let me go ahead and then write this out. So the Laplace transform of the derivative of a function y prime of t, this is equal to what? This is now multiplying diagonal terms, that is going to be e to the negative st, and this is multiplied by y of t. We are taking the limits of integration from 0 to infinity. We are done with the integration here. And now negative, when you multiply them, that becomes positive, right? So that is going to be plus e to the negative s times e to the negative st. And this is the integral from 0 to infinity, because when we are multiplying terms horizontally, we will have to take the integral, and then this is multiplied by y of t like this, and then dt. Alright, cool. So now let's evaluate the limit. So the Laplace transform of y prime of t, and this is equal to, so when we take the limit, so let me do it here. So the limit as t goes to infinity of e to the negative st, and this is multiplied by y of t, minus, we plug in 0 as the lower limit. This one is going to be 1, because this s is positive, and the power is going to be 0. So e raised to the power 0 is 1 multiplied by y of 0 like this. Cool. And now I'm going to have plus, this s is a constant in the t world. I'm going to pull it out of the integral. Then I have the integral from 0 to infinity of e to the negative st, and this is multiplied by y of t and then dt. Right, so as t is approaching infinity, this one is going to be approaching negative infinity because s is positive, and everything here is going to be approaching 0 because 0 times this one is 0 regardless of what this one is, right? So the Laplace transform of y prime of t, this one is equal to 0 minus that is going to be negative y of 0, and then plus s, and this one is the definition of the Laplace transform of y of t. If we go back here, so the Laplace transform of y prime of t is the integral from 0 to infinity of e to the negative st times what we want to transform, and this one here is the same thing. The Laplace transform of y of t, the integral from 0 to infinity of e to the negative st times what we want to transform. So this one is the Laplace transform of y of t, and the Laplace transform of y of t is the same as capital Y of s, where s is our Laplace variable. So this one is s, and this one is capital Y of s. That is the Laplace transform of y of t, and now minus y of 0 like this, and this one is the Laplace transform of y prime of t like this. All right, cool. So now this is what we have. So this is the Laplace transform of y prime of t. Cool. So now this is the first derivative. What if we want to take the Laplace transform of the second derivative of the function y of t? So let's say y prime prime of t. What is the Laplace transform of y prime prime of t? Let me switch colors, and then I'll show you how that is done as well. So we want to find the Laplace transform of the second derivative of a function, that is y prime prime of t, like this. And this one is equal to the integral from 0 to infinity of e to the negative st, and multiply by what we are seeking to transform, the second derivative of the function y of t, like this. Cool stuff. Now what do we have here? So what can we do here? So we have to integrate this one. That is obvious. Now to integrate that, we have to use integration by parts, but we have to do this one twice. So let me switch colors again, and now we look at the integration by parts, the tabular method. So the D for differentiation and I for integration, I am going to differentiate e to the negative st. So this is plus, next one is negative, and the next one is plus, continuous like this. And now differentiating e to the negative st with respect to t, that is going to be negative s e to the negative st. Differentiate this one again with respect to t, that is going to be positive s squared, and then e to the negative st, like this. Cool. Now what about integrating the rest? The rest one is going to be y prime prime of t, right? So this is what we have. So integrating y prime prime of t, we are differentiating this one twice, and now we want to integrate it for the first time. So remember, integration is anti-derivative. So the first integral is going to remove 1 prime, leaving 1 prime. So that's going to be y prime of t, like this. And we integrate again for the second time. So the integral of y prime of t is y of t, because integral is anti-derivative. So this is what we have, and now we will have to multiply diagonal terms. When we multiply diagonal terms, we are done with the integration. We just take the limits of integration, and that is it. But when we multiply terms horizontally, we will have to take the integral. So that is the drill for integration by parts. Let me switch again. Now the Laplace transform of y prime prime of t, this is equal to what exactly? So now let's multiply diagonal terms. So the first one is going to be this guy, right? So that is going to be e to the negative st, and this is multiplied by y prime of t. Next is going to be these guys, right? So this one is going to be negative, negative, that is going to be positive. And now we are going to have s e to the negative st and multiplied by y of t, like this. Cool. Now here we are done with the integration. All of this we are done with the integration. We take the limits of integration from 0 to infinity. And now because we want to multiply terms horizontally, we will have to take the integral. So we have plus the integral from 0 to infinity. Now let's multiply terms horizontally. So that is going to be s squared. I'm sorry, this is s squared. So that is going to be s squared, and then e to the negative st, now multiplied by y of t, and then dt. Cool. So this is the integration by parts. So the headache is taking the limits of these guys. Now let's do that. So the Laplace transform of y prime prime of t, this one is equal to, now let's plug in the limits. So we will have this, the limit as t goes to infinity, which is the upper limit of e to the negative st. This is multiplied by y prime of t, and now plus s e to the negative st, and now y of t, like this. This is the upper limit minus the lower limit. What do we have? If we plug in the lower limit, this one is going to be 1, because e raised to the power 0 is going to be 1, and 1 times this, that is now going to be y prime of 0, like this, because when you plug in 0, that's going to be y prime of 0. When we come here, when you plug in 0, that is going to be what? Remember, this is minus everything here, because that's the lower limit. And now if you plug in 0 here, that is going to be, this one is going to be s multiplied by 1 multiplied by y of 0. Right, so this one is going to be plus s, and this is multiplied by 1 multiplied by y of 0, like this. So this is the lower limit and the upper limit. And now you add the integral. I'm going to continue from here. And now this s squared is a constant in the y world, in the t world, I beg your pardon. So that's going to be s squared, and then the integral from 0 to infinity of e to the negative st, and this is multiplied by y of t and then dt. Cool stuff. Now we will have this, the Laplace transform of y prime prime of t. This is equal to, now as t is approaching infinity, because s is a positive number, this one is going to be approaching 0, this one is going to be approaching 0, and now everything here is going to be 0 regardless of what y prime of t and what y of t is. So when you plug in infinity, that's going to be 0. So we are going to have 0 minus y prime of 0 minus s times y of 0, like this. And now plus s squared, which is this guy here, times this. This one is the Laplace transform of y of t. Laplace transform of y of t, like this. Cool. And Laplace transform of y of t is capital Y of s. So the Laplace transform of y prime prime of t, this one is going to be, this one is s squared multiplied by capital Y of s, and now minus y minus s times y of 0 minus y prime of 0, like this. This one is the Laplace transform of the second derivative of the function y of t. Cool. So this is what we have after using the Laplace transform to find a derivative of some functions. So with this one, do we observe a pattern that we can just write the Laplace transform of y prime 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 of t without using the definition and solving the integral? So this is the Laplace transform of y prime of t. That is s times y of s minus y of 0. That is the initial condition. So what if we want to write the Laplace transform? What if we want to write the Laplace transform of y prime 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 of t? That is the third derivative of the function y of t. So remember, see the pattern. The pattern here is that when we have this, the second derivative, this Laplace variable is going to be squared multiplied by the Laplace transform of the function y of t. So this one is going to be s to the third, right? Because we have the third derivative, right? And this is going to be multiplied by the Laplace transform of the function y of t, which is capital Y of s. And now next one is going to be minus s. So the s is going to reduce by a power 1. So the next term is going to be s squared. So here it was s squared, and now the power reduced to 1. That is s raised to the power 1. That is what we have. And now for the third derivative, because this one is squared conforming with the number of times we differentiate, so the next s here is going to be s squared reduced by 1 until it gets to 0. So this is going to be s squared, but it's going to be multiplied by the first initial condition, which is y of 0. And now next one is going to be minus, is going to reduce by a power 1 again. So that's s raised to the power 1. And that is going to be multiplied by the first derivative, y prime of 0. And this one, the s continues to decrease in power. And that is s raised to the power 0. Now we're going to have y prime prime of 0. Like this. So differential equations, if we have like the third derivative, the initial condition will only exist up to y prime prime, the second derivative of the initial condition. So rewriting this one is now going to be y prime 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 of t. The Laplace transform of that is going to be s to the third, and our capital Y of s minus s squared times y of 0 minus s times y prime of 0 minus y prime prime of 0. This is the Laplace transform of the third derivative of the function y of t. Now, to generalize this, how can we generalize this? So let me generalize this one for you to see. So if you have the Laplace transform of the nth derivative of the function y of t, so the nth derivative, that means the s here is going to be raised to the power n. Then you are going to have the Laplace transform of the function y of t. And our next one is going to be s raised to the power n minus 1. But we don't know what n is. N can be a very large number. So we will have to just use the formula to approximate this. So this one is going to be minus because all these ones are negative, right? Then we are going to have the summation. Let's say k running from 1 to n, right? And then we are going to have s raised to the power, because n is reducing by 1 for each subsequent term, that is going to be s raised to the power n minus k. And now we will have these ones too are increasing, right? The y prime, but they will never increase up to the point of the number of derivatives that we are having. So the last one here is y prime, but what we have in our initial what we are taking the Laplace transform of is y prime. So this one is going to be multiplied by y raised to the power k minus 1, like this, of 0. This one is just, it's not a power, this one is the derivative. So this one here is the derivative, the order of the derivative, not just the power. Right, so this is the general formula for the Laplace transform of the nth derivative of a function y of t. Alright, cool. So now remember when I started, I said how can we use Laplace transform to solve a certain differential equation? So the whole essence of this exercise is to be able to use the Laplace transform to solve differential equations, which is very important. So now going back to this one, let's use the Laplace transform to solve this differential equation with this initial value problem. So remember, without the initial value condition, we can't use the Laplace transform to find the solution to this differential equation. So now let me go down there and then we solve that using the Laplace transform. Okay, so now just to remind you, so the Laplace, the differential equation is y prime of t minus 2y of t, and this one is equal to 0 with the initial condition that y of 0 is equal to 1, like this. So this one, you can really solve this one using separation of variables, but let's use Laplace transforms here. So we will have to take the Laplace transform on both sides of this differential equation. So let's do that. So the Laplace transform of y prime of t, right, minus 2 times y of t, like this. This is equal to the Laplace transform of 0. So the Laplace transform of 0 is 0, so the right hand side is 0. But this one, using the linearity property, this is the Laplace transform of y prime of t, right, minus 2 times the Laplace transform of y of t. And this is equal to the Laplace transform of 0 is 0. Now, what is the Laplace transform of y prime of t? We have found that, so I'm just going back up here to pick it up. So the Laplace transform of y prime of t, this is s times capital Y of s minus y of 0, right? So this one is s times capital Y of s minus y of 0. That is the Laplace transform of y prime of t. And now minus 2 times the Laplace transform of y of t. This is capital Y of s. And this one is equal to 0, the Laplace transform of 0. Now remember the initial condition, y of 0 is equal to 1. So let's just replace this one with 1. And now we are going to have s y of s minus 2 y of s, right? And now we have minus this one is 1. So that is going to be 1, and that is equal to 0. Now you can take negative 1 to the other side, and that is going to be, you can factorize s out here. I'm sorry, that is y of s. So this one is going to be s minus 2, and then you are going to factorize y of s, and this is equal to 1. So let's isolate y of s. So we can divide both sides by s minus 2, and that y of s is going to be 1 all over s minus 2, like this. What we have to do is to now take the Laplace inverse of this function. So now we have to take the Laplace inverse of y of s, like this, and we do the same thing to the right hand side, the Laplace inverse of 1 over s minus 2, like this. So taking the Laplace inverse of capital Y of s, that is going to return y of t, and this is equal to the Laplace inverse of 1 over s minus 2. If we can recall, that the Laplace transform of e raised to the power at, this one is equal to 1 all over s minus a. With the condition that s is greater than a, that means that the Laplace inverse of 1 over s minus a, this one is going to return the function e to the at. So the same thing here, the Laplace inverse of 1 over s minus 2, that is going to be e raised to the power 2t, like this. And this one is the solution to our differential equation. So this y of t equal to e to the 2t is satisfying this differential equation. That is y prime of t minus 2 times y of t. This is equal to 0. In the initial condition that y of 0 is equal to 1. So you can verify that this one is the answer to this differential equation. Right, so you can just do a quick verification. Y prime of t, so if y of t is this, that means that y prime of t is equal to, just differentiate this, that's 2e to the 2t. Right, so differential equation, if you now plug everything here, will it be equal to 0 on the right hand side? So y prime of t is 2e to the 2t minus 2 times y of t, and y of t is e to the 2t. So e to the 2t, and you see that is indeed equal to 0, which is equal to what we have on the right hand side. So this is the answer to the differential equation, and that is solved using just Laplace transforms. So this is just a very simple example of a differential equation that can be solved using Laplace transforms. So in my next video, what I'm going to do, I'm now going to use these concepts to solve differential equations with initial value conditions that are much more complicated than this simple example in this illustration. So let me wrap it up here. So the Laplace transform of y prime of t, this is equal to s times capital Y of s, which is the Laplace transform of y of t minus y of 0. The Laplace transform of y prime prime of t, that's the second derivative, that is s squared y of s minus s y of 0 minus y prime of 0. We will be using this one a lot, right? But exceptional case, we can have the Laplace transform of y prime prime of t, and this one is equal to s to the third y of s minus s squared y of 0 minus s y prime of 0, right? Minus s y prime of 0 minus y prime prime of 0, like this, and we can generalize it for the nth derivative of this function y of t. So we will utilize these ones a lot in my subsequent videos. So if you really enjoy this video, you give me a thumbs up and subscribe to my channel for more of this. So in my next video, I'm going to use this result to now solve differential equations with initial value conditions. So I will see you in my next video.